What's up, YouTube? It's Trilla Manila. It is day 43 on the road to code, and today ended up finishing up the functional programming in JavaScript and Free Code Camp. So there is 2 more sections to complete, and we are done. I mean, definitely not mastered, but definitely got a pretty good understanding. From there on, I'm probably just gonna focus on doing projects for like about a week or so before moving on up to the front end development section. And once I'm done the front end development, I'm probably just going to do a few more projects and start applying for jobs. We'll start applying for jobs while I'm doing projects. That's how we're going to do it. So not too much longer. We're still in January here. Pretty exciting stuff. This is, seems like I've been doing this for like a minute, but it really hasn't even been that long. It's 43 days. Yeah. But let's just get right into it. Let's get a refresher on functional programming. I found this blog here, this blog post, just explaining what it is. And let's just get right into it. It's a bit of a longer format. It says 11-minute read here. So let's just get right into it. Alright, introduction to functional programming. Functional programming, often abbreviated as FP, is a programming paradigm that heavily utilizes functions to change how application state is managed. It is declarative rather than imperative, meaning programming in a functional manner tells your code what to do rather than telling your code how to do it. Alright, tells your code what to do rather than telling your code how to do it. Alright, interesting. Like how they put that. Functional programming has a very steep learning curve, mainly because it's a very different than how most applications are written. However, once the basic patterns are learned, programming with the FP paradigm tends to result in more stable applications because of its predictability. This article will break down FP into 3 concrete steps. There's a lot more than just 3 steps, but this will give you a great start in learning how FP works. Alright, so the 3 steps here are pure functions, functional composition, and currying. Pure functions. Pure functions are simply functions that take an input and generate an output. They do not perform any side effects, given that the same input to a pure function, you can expect the same output. Run the same input through the same pure function and you should always get the same answer each and every time. Alright, here's an example of a pure function. Const add equal x equal or greater than x plus 2, add 2, always get 4, add 2, still 4, add 2, still 4. Alright, when you call add 2, you get 4 no matter how many times you call it. Alright. However, here's an example of an impure function. Let y equal 2, const add equal x equal to or greater to x plus y, add 2, get 2 at first, while y equals 5, add 2, now you get 7. Alright, good explanation there. Since the add function depends on y, which is an outside of the scope of the function, it is considered impure. Its output can change because of the function does not only depend on its own arguments. Another factor of pure functions is that it does not cause any side effects. That is, anything outside of the scope of the function stays the same. Here's an impure function that breaks that rule. Let y equal 2, const add equal parentheses open parentheses equal to or greater than y plus 2 plus equal to, add equals 4, and add open parentheses equals 6. Alright, when writing pure functions for the purpose of functional programming, you want to be sure that any output is derived deterministically from the function's argument and immutable constants. For example, you could have a constant called pi to store the transcensional number, and your function can depend on it because that number is not going to change. Usage of pure functions is essential to understanding functional programming. If the state is changed outside of the function, a lot of bugs can be introduced due to impurity. Now, if you're a web developer, it's almost impossible to write everything in pure functions. For example, a simple console log is considered a side effect. Any function with a side effect is, by definition, not pure. A console log is a pretty harmless side effect, but what about doom manipulations. What if I want the results of my mapping function to be written to the DOM? Do I need to pass the entire DOM in as a function and then return the new DOM out? Well, that's one of the purposes behind libraries such as React and Vue. They wrap up all the DOM manipulating side effects into the library so that DOM can be written to deterministically as a function or prop or state, and you can still use the pure functions to produce React or Vue components. Functional composition, this is the second step here. One of the main allures of functional programming is the fact that it allows you to compose functions. That is a fancy way of saying put the results of function in another function. It could look like this: const add 10 equal x equal or greater than x plus 10. Const double equals x equal or greater than x times 2. Add 10 parentheses double parentheses 5, and then close that out, equals 20. Alright, we can use the function called compose to express functional composition. Here's a simple compose function. Const compose equal parentheses dot 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 fns parentheses equal to or greater than arg equal or greater to fns dot reduce parentheses acc comma fn parentheses equal to or greater to fn parentheses acc parentheses comma arg, and then closing out parentheses there. In case you're unfamiliar with the spread operator, we're allowing compose to take a variable number of arguments, and we store that in an array we are naming fns, the compose function that takes in a bunch of functions and then returns a new function that takes in the argument. Then the reduce functions sequentially calls each other from left to right, passing the arg first, then passing that result into the next function. By using this compose function, we can now create new functions with it. Const add 10, then double equal compose parentheses add 10 comma double parentheses. That's an example there. Now be very careful, the order of things can get very confusing. Note that the equivalents of the functions add 10 parentheses double parentheses 5 equal double, then add 10 parentheses 5 equals true. It may seem backwards, but your code actually goes from the innermost to the outermost parentheses. Remember, PEMDAS or BODMAS from elementary school. So for add 10 parentheses double 5 parentheses, it doubles 5 first, then adds 10. When doing functional composition, we compose them in the order of computation, not in the order of writing when we write out our code. However, it should be simple enough to write a function that applies to compose functions in reverse so that it appears in the same order as writing the code. Alright, third final step, currying. Sometimes we want to compose functions that take more than one argument. How is that possible? For example, if I take a basic mathematical function, const add equal parentheses x comma y equal or greater than x plus y, I like to be able to compose a bunch of these arithmetic functions together, but how? This is where the concept called currying comes in handy. Currying converts a function that takes in certain numbers of arguments, which is called its arity, and if supplied fewer arguments than it takes, return a new function that takes in the rest of the arguments. This may sound bizarre, so here's how we would curry the arithmetic functions above. Const add equal x equal or greater than y equal or greater than x plus y. Now we can use functional composition to perform any amount of arithmetic chaining. Compose parentheses add parentheses 5 comma subtract parentheses 1 comma multiply parentheses 4 comma divide parentheses 2 parentheses 1 equals 10. Alright, however, what if we want to do a more complex function that takes in more than just two arguments? Const sum equals parentheses x parentheses x comma y comma z equal or greater than x plus z plus y. Alright, and then const curried sum 0 question mark operator equal x equal or greater than y equal or greater than z equal or greater than x plus y plus z, or alright, now it's given different possibilities here. The answer is it could be all of the above. You should be able to call a carried function with arguments in the same list or applied separately like so. Carried add parentheses 3 parentheses 4 equals 7. Carried add parentheses 3 comma 4 equals 7. Carried sum parentheses 1 comma 2 comma 3 equals 6. Carried sum parentheses 1 parentheses 2 parentheses 3 equals 6. Okay, so it's just showing how it's all the same. Thankfully, just like there's compose function we made above, there's also a curry function. Here's a simple implementation. Const curry equals parentheses uncurried fn comma dot dot args, which is arguments, equal or greater than, and then curly brace. Oh, is this all part of it? Well, I'm gonna just stop right there. Of course, this only works if there are 0 optional arguments. Every required argument of the function you wish to curry must be named for fn length to work. If there are many optional arguments, then currying will not work. This is why some functional libraries like Lodash or Ramta split the erratic functions into multiples. For example, Lodash regular get function, which accepts 2 arguments, 3 with a default, is split into get or in the functional variety of the library. Now we can do functional composition to use our new sum function. And that's just more examples, and it's really long examples, so I will just be reading it to myself. It's just going to be reading out a list, which is already confusing enough for you guys. Which I will be studying all of these. Like I've been studying all the terms and syntaxes on a flashcard, which I feel helps a lot more than just writing it down in my notebook, because I go back to the flashcards and memorize it front to back, and it's just a lot more useful. Alright, the reduce function. The reduce function may be familiar to anyone who uses Redux before. After all, it runs on reducers. The reduce function operates on an array, and it contains an accumulator. This could be a sum, it could be an array, it could be an intermediary, results, a functional composition. The point of Redux is that it's extremely versatile. In fact, I'll leave it as an exercise for you to recreate, map, and filter using the Redux function. The simplest way to show how the reduce function works is by using a sum. First, the beginner way, const nums equals brackets 1, 2, 3, 4, 5, let sum equals 0, and then this is a for loop, a for parentheses let I equals 0, a semicolon I less than nums dot length, semicolon I plus plus, and curly brackets sum plus or equal nums brackets I. Alright, as mentioned before, this leads to an impure functions. We define a sum and it changes over time. We don't want that. With reduce, we can specify our starting point, and then we can specify what we do want at each step of the iteration. Nums.reduce parentheses accumulator dash num parentheses equal to or greater than accumulator plus num comma 0 parentheses. Alright, this starts the accumulator at 0, and at each step we pass the return value of that accumulation function as accumulator for the next iteration. We will see the following logs: iteration 0, accumulator 0, number 1, iteration 1, accumulator 1, number 2, iteration 2, accumulator 3, number 3, iteration 3, accumulator 6, number 4, iteration 4, accumulator 10, number 5, final sum 10. Okay. Alright, so this is just a bunch of code, which is not good way to read it off to you guys, because it's going to be confusing since you guys aren't getting the visual. So I'm going to just read this, skim over it. Then I'm going to just keep reading on. As you can see, by keeping the reducer a function of a state and an action, we can maintain a history of all of our states, and we can even time travel and see what would happen if we use a different action at a specific point in time. This makes Redux really simple to test, because once you know the inputs, the output should be predictable. By the way, Redux example above is a perfect example of where I would use currying and functional composition. Let's say I want to keep track of the counter and how many times the user clicked the button, any button. I'm going to use a function called set, which is curried function that takes in the key, the intended value, and the object to update. It does so in a mutable manner without mutating the original object. The set function can come from the low-fp library, but I've implemented it myself to reduce the amount of magic going on. And he's shown an example of coding how to count the buttons clicked. And moving on, as you can see, whenever the action.type matches, we pipe the state through the functions passed into the compose function. It's like calling set counter plus one state, then set parentheses times clicked plus one on that new state. Some real world examples. I use functional composition all the time in my Node.js and React.js apps. For example, to parse a URL like users /me $API key equal foo, you could use a function like this: const curly braces flow comma split comma head tail filter curly braces equal require low dash. Alright, it's a bunch of code again, but I do like how this guy is putting in a lot of real world examples of using code. Like I'll definitely be using, like I know I'm definitely going to be using Node.js and React.js for front end jobs. And yeah, the parse the URL. And then another example of code was counting how many times a button was clicked. That seems useful as well. So I do appreciate that. Alright, but continuing on, this will return an array that reads something like users-me, which I can use a query resource or do whatever I want. Flow works like compose. I preferred it to compose because low-dash native compose function goes from right to left, which is weird to me. Note that we could write a function called isTruthy and make it something like v equal or greater than v. Then we can use filters, parentheses isTruthy, to make our code read a bit better. However, though not entirely necessary, that's one of the options that are available to you in FP. I've also used this to work with large data sets using high-chart libraries. And this is more example of real code, which is pretty long, so I'm not going to read it out to you guys. Alright, pass in a series of data. It will average all the y values of all the points that are inside the viewport. Highcharts does that for me, but I have to actually make the average calculation. Both of these examples take advantage of pure functions. None of these functions, composed or otherwise, mutate any data outside of the scope of the function. Functional composition and currying. By keeping these three concepts in mind, you should be able to convert a lot of your code into cleaner functional code. Alright, again, really appreciating the real world examples of all this. But then here we are, wrapping it all up. I hope this introductory post was helpful for you to understand how functional programming works, to test your newfound knowledge. Yeah, that's pretty much it. I mean, there's a question at the end here. Oh man, I read like a real low-key blog. It's only one clap on Medium. Well, it is what it is, but yeah, that's pretty much today's assessment. Day 43, Road to Code, 100 Days of Code Challenge. We are halfway there almost. And yeah, that is it. Just follow my blog at trillamanila.com, Twitter at trillamanila as well. Have a good day.
Trilla Manila!